Welcome back. This is the second part of my MATLAB V-REP integration video. If you haven't done the first part, please go back because it's important that you do that for this simulation to work. This video I will try to gear towards someone who might be new to V-REP. In this video, we will add a few extra obstacles in the scene. I will then show you how to use the remote API functions in MATLAB so that we can control the actuators on the robot's wheels, read the sensors, and then we'll add a camera, and then we'll transfer the images from V-REP into MATLAB. I will then also show you how to extract the X and Y position of the robot into MATLAB as well. Let's begin. One thing that we need to do in the scene is to disable the behavior of the Pioneer P3DX. Currently, it moves when the simulation is started. However, this behavior will interfere with our MATLAB commands, so we have to disable it. This is the associated child script that I'm talking about. If you click on Tools and Scripts, or push this button right here, you'll see a list of all the scripts currently active in the simulation. Select the non-threaded child script for the Pioneer and select Disabled. Now, when we run the simulation, the Pioneer does not move, and we are ready to send commands from MATLAB to the wheels. Let's turn our attention to MATLAB and create our very own MATLAB script. I'm going to grab a few commands from the simpletest.m. The first one creates a remote API object and calls it V-REP. The second one is vrep.simxfinish, and it just closes any currently open connections. The third command is vrep.simxstart, which creates a connection. It uses this IP address, which is just a local host, and then on this particular port. I'm not sure what the other commands are, but I can look them up within the remote API functions in MATLAB. When I search it, it tells me exactly what these other parameters are. I am currently satisfied with these numbers. If no connection can be established, the client ID will be -1. So what we have to do is we have to check with an if statement. So if it's greater than -1, then the connection was successful. And then we can add our code here. And then after the code has been executed, we want to close the connection by running the vrep.simxfinish command. And then at the very end, what we want to do is we want to call the destructor, which is the vrep.delete. And now we can save the script, and this is the barebones script that we will be using to further add code into this tutorial. Before we can get the wheels spinning, I need to introduce the concept of a handle. In V-REP, in the scene hierarchy, we see all of these diverse types of objects. There are shapes, actuators, or proximity sensors. Each one of them have unique properties which we can access if we know the object handle. Let's consult the remote API function list for a function called simxGetObjectHandle. Under MATLAB synopsis, it tells you exactly how to use it. It tells you what its return values are and what its input parameters should be. We're going to use this function. The first output parameter will be a number called return code. If you look under MATLAB return values, a return code is essentially a number that will tell you whether the function has executed fine. If it returns 0, then everything is alright, and then there is a bunch of other events. The next return parameter is the actual object handle, and we're going to call it left motor because we want to access the motor of the Pioneer P3DX. Also, we need to call the function vrep.simxGetObjectHandle because the simxGetObjectHandle is a function within this vrep object that we defined up here. As input, it requires the client ID, which we have defined up here. Then we need a string, which is the object name. In the vrep scene hierarchy, every single object is uniquely named, and we can use the name to access the handle. We want the Pioneer P3DX left motor. And finally, we need something that's called an operation mode. Again, let's consult the remote API function list for that value. Under operation mode, it says a remote API function operation mode. Recommended operation mode for this function is simx op mode blocking. If we read further into it, what the blocking mode is, the command will be sent and the function will wait for the actual reply and return it. There are other different ways, for example the non-blocking mode, which uses simx op mode one-shot. However, as per recommendation, we're going to use simx op mode blocking. And to access that, we need to use, say, vrep.simx op mode blocking because that variable is part of the vrep object. And now, if we run this line, we will get a handle to the left motor, which will be stored in the left motor variable. Let's do the same thing we did to the getObjectHandle command to the command that sets a joint target velocity. In the remote API function list, there is a command called simx_set_joint_target_velocity, and we're going to copy and paste the MATLAB synopsis into MATLAB. The function returns a return code. We have to preface it with vrep dot. Client ID will be the same as above. Now for the number joint handle, we're going to now use left motor. For the target velocity, let's pick 0.1 and then the operation mode. The function list recommends op mode one shot or streaming. However, when I tried it, it did not work for me. So instead, I'm going to use the blocking mode. We want the left motor to spin for, let's say, 5 seconds. And then we want to turn the actuator off. So we'll send 0. For this to work, vrep has to be running. And now let's run the code. And you'll see that the robot starts to move. It's only the left motor that's spinning it, and then after 5 seconds it stops again. Now that you know how to send actuator commands, let's retrieve some proximity sensor readings. First, let's clean up the code a little bit. I'll make a section for the handles and a section for other code. I'm also going to suppress the output, such as it is here, by putting a semicolon at the end of every command. Now we need to know the name of the sensor that we want to retrieve the handle to. The Pioneer P3DX, if you scroll all the way down, has 16 different ultrasonic sensors. And they're located around the top and around the circumference of the robot. If you click on the sensors, it'll show you the corresponding coordinate frame. The blue line is the z-axis and it's perpendicular to the face of the sensors. The Pioneer has 2 different front-facing sensors, and they're slightly at an angle to each other, and for no particular reason, I'm going to pick ultrasonic sensor 5. I'm going to copy and paste this command, and I'm going to rename it to ultrasonic sensor 5. And I'm going to store it in front sensor. This code is by no means pretty, but it's only there for illustrative purposes. And now we have a handle for the sensor, and we can go ahead and read it. I will modify this code slightly so that we can read the sensor better. Instead of this pause for 5 seconds, I'm going to replace it with a for loop. And this for loop is going to run for 5 seconds, except every 0.1 seconds it will execute a command. The other thing that I forgot to do, if you have been following this tutorial, I forgot to set the cuboid properties. If you double click on this cuboid symbol, go into Common, you need to set the object special properties to detectable. Otherwise, this object cannot be detected by sensors. To read the proximity sensor, we need to use the simx read proximity sensor command. If you take a look at the MATLAB return values, it actually returns quite a lot of different values. There's the detection state, the detected point relative to the sensor reference frame, the handle of the detected object, and the detected surface normal vector. If this was a real proximity sensor, you would actually get none of this. The only thing you would get is an approximate distance from the sensor to whatever it is that it's detecting. So we'll actually discard most of these values. I'm going to copy the MATLAB synopsis and paste it outside of the for loop. We want the return code. We also want the detection state. That way we know if something has been detected. We'll also keep the detected point. However, the detected object handle I'm going to replace with a tilde, which means that MATLAB is going to not store that information. And I'm also going to not take the detected surface normal. Let's preface this command with vrep.simxRead proximity sensor. We use the same client ID. Under sensor handle, we want to use front sensor. Now, as far as the operation mode goes, let's take a look what the function recommends. On the first call, it recommends to use simx opmode streaming, and then on the next calls, it recommends to use simx opmode buffer. What this does, it tells VREP to start streaming that information, and then on the following calls, MATLAB will retrieve the buffer. Outside the for loop, we're going to use vrep.simxOpmodeStreaming, and from inside the for loop, we're going to use buffer. And I'm going to suppress the output into command window by putting semicolons at the end. The detected point will be relative to this coordinate frame right here. So what we want to do is we want to turn this vector into an absolute distance reading. So we're going to display in MATLAB the norm of the detected point to get the distance. And now let's run the code. First I'm going to start VREP, and then I'm going to run the code. And as you see, the distance starts to reduce as the robot gets closer to the target. The final thing left to do is to add a camera to the Pioneer and then transfer images from VREP into MATLAB. In VREP, select Add, Vision Sensor, and then Perspective Type. We now want to move it to the Pioneer, so select the Vision Sensor and the Pioneer, and under Object Item Shift, click Apply to Selection. This took the vision sensor and moved it to the Pioneer, to the location of the Pioneer. Now let's move the camera sensor up by 0.2 meters. And now we want to rotate it. We want to rotate it, so we click on orientation/rotation. And we want to rotate it around its own frame, around the y-axis, by 90 degrees. And now, because the y-axis is usually associated with the vertical side and the x-axis is associated with the horizontal side, we want to rotate the camera by 90 degrees around its own z-axis. We can double check whether the camera output is correct by right-clicking anywhere in the scene, select Add Floating View, and then with the camera selected, right-click on the floating view, select View, and then associate view with selected vision sensor. Once you run the simulation, you will see that the camera cannot see the cuboid. However, it can see a little bit of the Pioneer and the floor. If we double click on the cuboid under Common, since we do not have renderable checked, the camera cannot see the cuboid. So let's select renderable. Now we run this simulation again and we can see the cuboid in here. The resolution of the vision sensor is currently pretty bad. Let's add that. Let's change that. Let's set it to 64 by 64. And then we can run the simulation again, and now we can see that the resolution is higher. The higher the resolution, the slower the transfer from V-REP to a remote API system. And then finally, what we want to do is we want to attach the vision sensor to the Pioneer, so we just take it and we drag it to the Pioneer. And now we have added a camera to the Pioneer robot. To transfer the images between V-REP and Matlab, we're going to essentially do the same thing we did with the proximity sensor. First, we're going to retrieve a handle to the vision sensor. We're going to call the variable camera, and the name of the vision sensor is simply vision sensor. Next, we're going to need a function to get the vision sensor image. And we have two options. The first one retrieves the image vision sensor as a pointer, and the second one retrieves the image as an image array. We'll want the second one. The other thing we should note is that we have an option of either receiving a grayscale image or an RGB image. And the operation mode that the function recommends is to first initiate streaming and then use buffer. The function returns the return code, the resolution, and a matrix of the image. We'll want to use the same client ID, and we want to use the camera handle. And for options, since we want a color image, we're going to use 0. And we'll use vrep.simxOpMode streaming as the operation mode. Make sure that you put a semicolon at the end to suppress the output of the image array into the command window. And then we're going to also put the function into our for loop. And we'll change the operation mode to just retrieving the buffer. And we'll also make sure that we display the image. Now let's test this. We'll run the simulation and run Matlab. And you'll see the image, and depending on the resolution, you can see the robot turning. The thing is, we picked a resolution of 64 by 64 pixels, which is quite small. Let's go into V-REP and change the vision sensor resolution so that we can see more detail. The simulation has to be stopped, and you can click on the vision sensor, and let's pick 256 by 256. The other thing that we want is we would like to retrieve a grayscale image. And now run the simulation and run MATLAB. And you'll see in figure 1 that the robot is turning and that the image is grayscale with a higher resolution. You might have noticed that our 5-second MATLAB for loop took longer than 5 seconds to complete. I'm going to test this out by running the for loop for only 2 seconds, and I'm going to use the tick and talk command to display the MATLAB time as the for loop is running. And when you run it again, you will note that our 2-second for loop takes over 5 seconds to complete. Remember, we're using MATLAB and V-REP in asynchronous mode, meaning MATLAB and V-REP do not actually wait for each other and send commands back and forth. If you have a simulation in V-REP that either uses a quadcopter or some kind of a balancing robot which requires exact command inputs, then asynchronous mode is not for you. I recommend that you take a look at the remote API modus operandi in the V-REP help file, or you can also consult the synchronous test example, which is located in the V-REP installation directory. If the exact synchronization is not important to you, then I would recommend that you keep commands that are computationally heavy out of MATLAB. If you wanted to fix this particular for loop, all you have to do is comment out the IamShowImage line, which is very computationally heavy. If you run this code again, you will see that this for loop finished in 2 seconds. I have now shown you how you can connect V-REP to MATLAB. I have shown you how MATLAB can send actuator signals and how it can also retrieve proximity sensor and image data. I hope this tutorial was of help. I would recommend that you spend a little bit of time in the remote API function list to find out what is possible with MATLAB. If you have any comments, please leave them in the comment section below. Thank you for watching.